Okay, so we're going to start chapter 10 today. Chapter 10 is about parametric and polar functions. So when we use this term parametric function and polar function, it's not really a class of functions like we talked about in our Algebra 3-4 course, where we talked about like quadratic functions and logarithmic functions and exponential functions. Those are all like classes of functions. When we talk about parametric functions, it's a way of representing a function. So like in your Algebra 3-4 course, what we talked about were these functions represented in what we'd call Cartesian form, where we have y equals, and then the function described in terms of just x's. Parametric and polar functions are described differently. They can still represent the exact same functions that we did in the Cartesian form, but they can also generate functions that we could not have using the Cartesian form. So they're a little bit more general or flexible, as you can create the graphs of things that you could not easily do in Cartesian form. Okay, so that's kind of the idea. In this first section, we're going to be talking about parametric functions exclusively. So in Cartesian form, we have one equation that's like y equals, and then a bunch of stuff in terms of x, right? Where we just have constants and x's on the other side, right? In Cartesian form, we're going to have two equations, one for x and one for y, where those equations are defined in terms of a third variable called the parameter. So for example, what we might say is we might say something like x is equal to t, y is equal to t squared, where t is just some value or all the values from the interval, say from negative infinity to positive infinity. So this is an example of a parametric function. And in fact, this parametric function is exactly just y equals x squared. It's the same thing. Now, there's a lot more writing that we had to do to represent that, but that's why that we can create functions that we could, or graphs that we could not using the Cartesian form, is we have more flexibility because we have a much more detailed description. Is everybody okay with that idea? Okay, so let's do a little bit of vocab dump here. So we say that the graph of the ordered pairs x and y, where x equals f of x and y is equal to g of x, are functions defined on an interval that we'll call I. So that graph is called a parametric curve. We say the two functions, f of x and g of x, are the parametric equations for the curve. We say the variable v or t is the parameter. And we say I is the parameter interval. So here we just have a little bit of a vocab dump where we're just describing the names for these different parts of our parametric function. So the graph that results from a parametric function we call parametric curve. We call the two different equations for x and y the parametric equations. We call the variable that those equations are in terms of the parameter. And we say that the interval over which that parameter is defined is the parameter interval. So let's look at an example of a parametric function. So let's say we have the parametric function x equals t squared plus 1 and y equals 2t. And we're going to show you how to use your calculator to graph this, and we're going to graph it over a couple of different intervals. So if you have your calculator with you, I'd invite you to take that out. And we'll show you how to graph a parametric function on your calculator. So I'll give everybody a second to kind of finish writing things down and take out their calculator if they're wanting to follow along. So the first thing that we're going to do is we're going to press the mode button. So if you press the mode button and you find the middle of your menu, you'll see that there's three options. One says func, and then par, and then pol, and then seek. You guys see that line that has those four options? Right now, all of your calculators are likely in function mode, because that's the mode really your calculator's been on really the entirety of your mathematics education, right? The next option, PAR, is short for parametric. That's what we're going to do now, is we're going to change our option to parametric mode. So move your cursor over to where it's on the PAR and press enter. to select that option. POL is short for polar. We'll do that later this chapter. And SEQ is short for sequential. We don't do that in this course. Is everybody okay with getting it into parametric mode? Worth letting you guys know, as long as we're here, we might as well change our angle format to radian from degrees. Probably every single one of us was in degrees prior to this because of the chapter we've been working in. We worked exclusively with degrees because we're talking about angle measures inside of figures. Since we're going to be graphing things here, radians are going to make more sense to be using. So as long as we're in here, let's change our calculator to radian mode also. Now, as a fair warning, I would say before you pack up and leave things today, to go back to your mode and change these things back. So before you leave today, I would put things back into degree mode and back into function mode. So on Thursday, when you take your calculator out to work on the test and you start getting wrong answers, you're not like, what is going on here? This doesn't even make any sense. Okay, so just wanting to give you a warning there and make a suggestion. Okay, so that's done. We'll exit out of there. Now, if I press the y equals button, you'll notice that the y equals menu looks a little bit different, right? For each function, we have an x equation that'll be written in terms of t, and a y equation that'll be written in terms of t. Now, you'll see that I had things here from the previous class, so I'm just going to clear those out. In x1t, I'm going to write t squared plus 1. To get the t, I'm just going to press the same variable button we pressed to get the x's. It's going to automatically put a t there because I've changed my mode to parametric mode. Because I'm in parametric mode, every time I press the x button, I'm really going to be getting a t. The calculator handles that all automatically for me. Everybody got that stuff typed in? Okay. The last thing I need to do now before I can press graph is to define the interval that I want to graph over. So in this case, I want to graph over the interval -3 to +1. Everybody okay with that? So to do that, I'm going to go to the window button. And where it says t min, I'm going to type -3. And where it says t max, I'm going to type +1. The t step, I'm just going to leave the way it is because it doesn't really matter as long as it's something like reasonably small, like 0.1 and whatever. It doesn't really matter there a whole lot. So whatever your t step is probably fine. And then before you go, why don't you just double check to make sure your x min is -10, your x max is +10, your y min is -10, and your y max is +10. Just our standard window that we'd be graphing over. So just scroll down and double check that those are also formatted there. Again, I don't know what the last thing we graphed in this class was. We might have changed our window to look at something. I frankly don't remember. It's been a minute since we've used our calculator to graph something. Okay. Everybody okay there? So I'm going to hit graph now, and this is what I get. Take a look at this graph. Did you notice anything strange about this? So it just stops. That's difficult to do when graphing in Cartesian form, to just have something stop midway and then go, right? Not easy to make the calculator do that. What else do you notice about this graph? Okay, kind of looks like a parabola, or part of one anyways. Sure. What was that, Olivia? It doesn't pass a vertical line test, right? Is it possible for us to graph things using a single equation in the Cartesian form that generate equations that don't, or graphs that don't pass a vertical line test? No. It's very easy to do that, though, in parametric form. This is one of the reasons why this parametric function representation is so much more flexible and versatile than the Cartesian one that we've been working with, is it allows us to graph things that we would not classify as functions in a Cartesian sense, but are perfectly acceptable in a parametric sense. Is everybody okay with that? Okay, so let's see what happens when we change the interval we're graphing from -1, or to the interval -1 to +2. So to do that, we'll go back to the window, and this time we'll change the x-min to -1. We'll change, the t-min to -1, and the t-max to +2. And then hit graph again. You notice we get something that looks quite different, right? Everybody's okay there? And then lastly, let's go ahead and change the interval again. So I'll go back to the window, t-min at -2, t-max of +3, and hit graph again. And again, I get a different picture. So that interval that we're graphing over matters a lot in terms of the graph that we're getting, right? What can we say, though, about all three of those graphs? They all don't pass the vertical line test, absolutely. But also, I would say that parts of them are all overlapping, right? If I draw all three of them on the same axis, parts of them would all overlap. You guys get what I mean by that? Yeah. If I were to graph this function over the interval -infinity to +infinity, that graph would overlap all three of them, right? So we're just getting different parts of this function, depending on the interval that we're graphing over. Does that all make sense? Okay, so let's look at another example here. So let's say we want to graph the parametric equations, x equals sine t and y equals cosine t. What piece of information am I missing? What haven't we been given that we should be given? The interval over which to graph, right? Now, even though we haven't been given this, looking at the two parametric equations that we have, we should be able to venture a reasonable guess as to what a good interval would be based on what we know about the equations x equals sine t and y equals cosine t. Does anybody feel like taking a little bit of a risk and venturing a guess as to what would be a reasonable interval to use? Okay, so we're using sine and cosine, right? So we're plugging values into sine and cosine. So think about what the graph of sine and cosine look like respectively. Do any parts of them repeat? Yeah, right? Like sine and cosine just do the same thing over and over and over again, right? What did we call the amount of time or amount of along the x-axis before the graph repeated? What did we call that? We called that the period, right? Does anybody remember what the period was for sine and cosine? 2 pi, right? 2 pi r is the circumference of a circle. Yeah, it was 2 pi. So it stands to reason the interval for t that I should pick should have at least the length of 1 period, so that we get all the possible values for sine and all the possible values for cosine. Everybody okay with that idea? So what do you think would be a reasonable interval that has the length 2 pi? What do you guys think? An interval that is 2 pi long. So an interval has a start and an end. So if you want it to be 2 pi long, well, that's going to be 4 pi long.
So it would be 3.14 is
Well, negative pi, 0 to 2 pi would be the easiest one to use. Negative pi to positive pi would be reasonable as well. That wouldn't have been a bad one, Andrew. Yeah, that's all I was asking for. Okay. So let's go ahead and take a look at what this looks like. Before we actually graph this, though, does anybody want to venture a guess as to what this graph is going to look like? You guys have all seen it before. Mm-hmm. Do you know any graph whose x coordinates and y coordinates are sine and cosine? The unit circle is correct. So it's not just a circle, it is the unit circle. So whether you knew it or not, when we defined the unit circle, what we really did is we created a parametric curve whose x-coordinate was defined as sine of theta, and the x-coordinate was cosine theta, and the y-coordinate was sine theta. That was a parametric function in terms of theta. You may. Is everybody okay with that one? So what I want to do now is I want to talk about converting between these two forms. So we know a lot about functions in Cartesian form. Really, the whole of our mathematics education to this point had been focused on functions in that form. We've just now been introduced to this new form called the parametric form. What we're going to do now is we're going to spend a little bit of time talking about how we can convert back and forth in between these two forms. So let's do a couple of examples. So let's say we have the parametric function x equals 2 minus 3t and y equals 1 minus t, where our t is on the interval negative infinity to positive infinity. When I look at my parametric function, how many variables do we see? 3. We have an x, a y, and a t. Everybody's okay with that idea? If we look at a Cartesian function, how many variables would a Cartesian function have? No. 2. It would have an x and a y. So my goal here is going to be to eliminate the t from this parametric function. Is everybody okay with that plan? So how do you suppose I'm going to eliminate the t? I'm going to solve one of the two equations in terms of t, and then substitute it into the other one. That'll give me one equation in terms of just x and y. Everybody's okay with that plan? Okay. So which equation do you want to solve in terms of t? X or y? Which equation do you want to solve in terms of t? The x equation or the y equation? Sure, okay. So what do I get when I solve this for t? One minus one, right? Okay. So I can then substitute that in to my x equals equation. Is that the form we usually write our Cartesian function in? No. What do we really want it to look like? Y equals. But that's not hard, right? We can just add the 1 over and then divide by 3. So now we're in Cartesian form. Yeah. For this one. Well, there's something else we should talk about here. So in parametric form, we're mostly concerned with the interval over which t is defined. In Cartesian form, we'd be mostly concerned with the domain and range. So let's talk about how we can get the domain and range from our parametric function. Okay? Okay. So the way that we can do this is I can look at the two parametric equations. So if I look at the x equals equation, I can use that to determine the domain. And if I look at the y equals equation, I can use that to give me the range. Everybody okay there? So let's describe how we're going to do that. So if I look at the equation x equals 2 minus 3t, that looks like an equation where x is the dependent variable and t is the independent variable, right? So I'm going to use the domain for t to determine the range for x equals 2 minus 3t. Okay? So what type of function is x equals 2 minus 3t? It's linear, right? Everybody agree with that? If I were to graph that on like a tx axis, you'd just get a line. Okay? And we're told the domain for this line is all real numbers. So what's the range for the line also going to be? Also going to be all real numbers. So the domain for my function is going to be also all real numbers. Now I'm going to do the same thing looking at the equation y equals 1 minus t. What kind of an equation is y equals 1 minus t? Also linear. The domain of that linear function is still negative infinity to positive infinity. So what would the range then be for that linear function? Negative infinity to positive infinity. So that tells me that the range for my function is also negative infinity to positive infinity. Okay. Let's do another example of this and finding these domains and ranges. Okay, let's say we have the function x equals negative 4t, y equals 2t squared plus 1, where t is on the interval negative 2 to positive 4. So if I want to get this into the Cartesian form, what do I need to do? I need to eliminate a t. So I need to solve one of these equations equal to t. Which one would be the easier one to do that to? The first one. Why the first one? Yeah, because there's not a squared, right? The squared makes that really kind of a pain. Everybody's okay with that? How do I square a fraction? Square the top and square the bottom. That's correct. And then how do you multiply two fractions? No. You multiply the tops together and you multiply the bottoms together, right? So that gives me 2x squared over 16, or reduces down to x squared over 8. That's how you solve a proportion. Cross multiplying. That's a solving technique, not a simplifying technique.
Oh, sorry.
That's okay. So here's our Cartesian form. Everybody okay there? Let's now determine the domain and range. Okay? Which of the Cartesian equations am I going to look at to determine the domain? The x equation. Okay. What is the domain for the x equals negative 4t equation? It is negative 4 or negative 2 to positive 4. Right? The interval for t gives you the domain for the parametric equations. So what is the key feature to a linear function like x equals negative 4t? That the function is always either increasing or decreasing, right? So if I look at the far ends of my domain, those are going to give me the highest point and lowest point on my function, right? So to figure out the domain, all I'm going to do is take those two endpoints from my interval and plug them in to my equation. So that tells me my domain is negative 16 to positive 8. Remember, when we write our interval, the smaller number always comes first, and the bigger number always comes second. So just because I found 8 before I found negative 16 doesn't mean I write the 8 first and then I give 16 second. Everybody's okay there? Which one of the two parametric equations am I going to use to find the range? The y equals equation. What kind of equation is y equals 2t squared plus 1? Quadratic. Okay. How do I find the range of a quadratic function? Okay, so it's either going to be the vertex to the all real numbers or the highest point, really, because we don't know that this thing goes. In fact, we know it doesn't go on forever because the domain for my function is only negative 2 to positive 4. Or what happens if it opens the other way? It could be from the lowest point up to the vertex, right? But that vertex is going to be really important. Everybody agree? Yes. So the three values that I care about in this quadratic are the endpoints of my interval and also the vertex. Let's find the vertex first. What is the vertex for y equals 2t squared plus 1? You should be able to look at that and tell me. No. The vertex is, well, in fact, all we really care about is the t coordinate of the vertex. So remember, for a quadratic function, the vertex, the x coordinate, is found by negative 2b, or negative b over 2a, excuse me. You guys remember that from your Algebra 3-4 course? Okay. So what is the the t coordinate of the vertex going to be for y equals 2t squared plus 1? No. 0. Why is it 0? The value for b is 0 because there is no just t variable. We only have the t squared. Okay. excuse me, guys. It is worth noting that we do need to check one more thing after we find that x-coordinate, or I'm sorry, the t-coordinate of the vertex. We did need to check that it does lie in the domain. Notice that 0 is in the interval from -2 to +4, so it does matter. If that weren't the case, we couldn't use it, but it does. It lies in there, so we're good. Everybody's okay there? Okay. And then I also need to check -2. See, that's 4, 8, 9. And then also check +4. So what is my range going to be? If I look at these three values, what's the smallest one? 1. And what's the biggest one? 33. So my range is just 1, 33. Okay. Does everybody feel okay on this one? Let's do another example. So let's say we have the parametric function x equals 3 cosine t, y equals 3 sine t on the interval from 0 to 2 pi. Are we going to be able to approach this problem the same way we did the previous one? No, why not? Because solving for t and then making a substitution is going to present some problems to us, right? Yeah. So that's going to be an issue. Okay. So what do we do then? Well, let's look at what the graph of this would be. Okay, so that's all set. What shape is the graph? A circle, right? It just looks like an oval because of the viewing window is rectangular instead of square. Who remembers what the equation for a circle is from their geometry course? Yeah, that was quite good. What does HK represent? Well, the center, and R is the radius. Okay. So in this picture that we have here, what is our center? Yeah, the graph on our calculator. Good, the origin. What is the radius? 3. Okay. So it appears that we should have x squared plus y squared is equal to 3 squared, right? Let's confirm that, shall we? So if I take x squared plus y squared, and I substitute in that x is equal to 3 cosine t, and y is equal to 3 sine t, and then we'll simplify and see if we can get 3 squared or 9 out of that. Sound good? So when I do 3 cosine t squared, I square the 3, and I square the cosine t. Same thing with 3 sine t squared. Everybody's okay with that? Notice that I have a 9 in common to each of those terms. So let's factor that 9 off. Does anybody notice anything here? Yeah, cosine squared plus sine squared is 1. So we're left with just 9, and that's what we're hoping to see, right? Since those now match. Isn't that nice? So again, depending on what you have, may not be convenient to try to find that Cartesian form algebraically. We might have to use some like previous geometric knowledge to kind of make that work. Okay? Let's now talk about going the other way. So let's talk about going from our Cartesian form to the parametric. Okay. So, how would you guys like to do this? You want to do this the hard way or the easy way?
Easy way.
Easy way.
The hard way. Are you kidding me?
Okay.
No, definitely easy way.
So, Joanna?
Oh, sorry,
No, stretch on. You can stretch all you want. I just
John.
looked like an arm, like a raised hand. That's okay. All right. So, how many times does x occur in this function?
No.
Just one time, right? Just has one place. So the easiest thing to do is just pick x to be t. What does that mean y has to be? Just 3t minus 2, right? Does everybody agree with that? There's one last thing we need, and it's the interval over which this function is defined, the parameter interval. This is the big advantage of choosing x to be t. So whatever the domain of x is going to be the same as the parameter for t, or the interval for t. So if I look at the equation, y equals 3x minus 2, what kind of function is that? Y equals 3x minus 2. What kind of function is that? Linear. Okay, what's the domain for a linear function? All real numbers. So that's going to be the same as my parameter interval, since x is equal to t. All the values that x are defined for should be the same as all the values t are defined for, since x and t are the same in this. Or we chose x and t to be the same. Is that okay? Quite a bit easier, right? Okay. We chose it to be that way because it makes the problem easiest. Yeah. And really, because the x occurred in one place, that's an easy thing to do. So let's say we wanted to write the parameterization of the line that passes through the 2 points here, A and B. When I say parameterization, what do I really mean? I just want the parametric function, right, of the equation for the line that goes through these points. So, what's one way we could do this? What's one way we could do this? Well, we could use the 2 points to write our slope-intercept equation and then convert that into the parametric form. That's no fun to me, though. Another way, we can use vectors. So, who remembers the vector equation for a line? You guys remember this vector equation for a line? Okay. So vector v, remember, is either the same as BA or AB, right? So slope-intercept. That's EQN? I know. And R naught then could just be one or the other, right? Everybody's okay there? You remember doing this just a chapter ago? That's a 7. 9 minus 2 is 7. Yes?
You should give us like all microphones to the video so we can hear us.
Oh my goodness, I think that's a terrible idea.
Like, be like, I agree. Like, are we okay with that? Yes, we are.
All right. So, excuse me, guys. So, this vector equation for a line is ostensibly the same as our parametric equation. So what is my x equation going to be? What do you guys think? What's the x equation going to be? Three plus 8t. What's the y equation going to be? Nine plus 7t. Okay, everyone, need you to refocus. We're getting turned around here. We need one more thing. What's the interval for the parameter? What are we parameterizing? The question asks for the parameterization of the line through these 2 points, right? What do we know about lines? And they go on forever in both directions, right? So stop talking, please. So what is the interval for the parameter going to be? Yeah. Okay. I guess we'll stop here. That's fine.